Hey everyone, welcome to STEM Time with Navya and Aishwarya. We are your hosts, Navya.
And Aishwarya. Our topic today is about data structures. So before we dive in, Navya is going to give you guys a quick update on the current event like promised.
So, from Science Daily News, the topic of the current event is stabilizing brain computer interfaces. And recently, researchers were able to develop a new machine learning algorithm that reduces the need for brain computer interfaces to undergo recalibration, which can improve their stability to remain stabilized during use.
Wow. So, a little disclaimer is that today's episode is going to be a little bit longer than usual because there's a lot of information we need to talk about that covers data structures, but unfortunately, it is all important in order to master computer science. So let's dive right in. The definition of data structures are that they are a specialized means of organizing and storing data in computers in a way that we can perform operations on the data more efficiently. So data structures also have a wide and diverse variety of usage across multiple fields like computer science and software engineering. But we're going to start off with the basic data structures we need to know.
So the first data structure we're going to go over is an array, which is a structure that holds items that consist of the same data type. So since arrays have a fixed shape, the process of inserting and deleting elements cannot be done straight away. In order to insert an element, you have to create a new array with an increased size, copy existing elements, and then insert new elements. To delete an element, the same process must be done, but starting with the smaller array size. An important thing to know about arrays is that it is possible to randomly access the data, and there are also many types of arrays, including an array of strings, an array of integers, and even an array of arrays, and a two-dimensional array. So moving on to the array operations.
So for array operations, there are three important ones to remember, and they include traverse, search, and update. So a traverse simply means to print elements by going through them. Search means to find an element in the array using the value or index. And finally, update is given an index, you need to change or update the value of an existing element. But before we move on to our next data structure, I think it's important we talk about the application of arrays. So arrays are used to sort algorithms, and they are one of the most simple components that is needed in order to build more complex data structures like heaps, vectors, and matrices. Matrices, sorry.
So moving on, the next data structure that is extremely important is a linked list. So a linked list is a sequential structure that consists of items in a linear order linked to each other. Now, this is different from arrays because you have to access data in order. So random access is not possible, unlike arrays. So let's dive into some more parts of a linked list and what they build into. Nodes are elements in a linked list. Next is the pointer to a successor node, and along with a key makes up a node. Head points are the first element of a linked list, and the tail is the last element of a linked list.
So a few examples of linked lists include a singly linked list, which means only going forward direction, a doubly linked list, which means forward and backward direction, and circular linked list. So that means it keeps going in a circular direction with head to tail and tail to head. And just like how our first data structure arrays had operations, so does linked lists. So search is one of them, and we've already come across it. It's to find an element given a key, but this time it's through a linear search. Our next component our next operation is insert, and it is to insert a key in the list, either at the beginning, middle, or end. And finally, our last operation is delete, which is the same thing as insert, but instead of adding something, you would remove an element. So finally, for the application of linked lists. When linked lists are being used in compiler designs for symbol table management and also to switch between programs using Alt and Tab.
So our next data structure is stacks. So a stack is also known as last in, first out structure, and it resembles a real-world stack, but is also found in many programming languages. Just like other data structures, stacks also has operations that include pop and push. To push means to insert an element on top of a stack. To pop means to delete the topmost element and return it. Other simple functions include peek, which is to return the top element of a stack without deleting. Is empty means to check the stack if it's empty, and then is full is to check whether the stack is full or not. And like always, here are the applications of stacks. They are often used for expression evaluation and to implement function calls in recursion programming.
Great. So this next data structure is one of my favorites, and it is queues. So queues is a first in, first out structure that is found in many programming languages. And the operations of a queue include enqueue and dequeue. So enqueue is to insert an element to the end of a queue, and dequeue is to delete an element from the beginning of the queue. And queues are applied in order to manage threads in multi-threading and also to implement queuing systems. So moving on to our next data structure, we're going to talk about hash tables. So hash tables are a data structure that store values with keys for each storage type, and it's very efficient regardless of the size of the data.
So why are hash tables used? They are efficient and it is used mainly to avoid direct addressing, which uses one-to-one mapping between values and keys that results in a huge table with a large number of key value pairs, which causes storage issues on a regular computer.
So now we're going to talk about how hash functions prevent direct accessing. So the hash function helps us calculate the index of a slot in the table to which each value goes in, and the value calculated by the hash function is called the hash value. So let's define some variables to help you understand the formula h of k is equal to k modulo m. So our first variable is h, which is the hash function. And our next one is k, which is the key of which the hash value should be determined. And finally, m, which is the size of the hash table and the number of slots available.
So if a collision ever occurs giving the same outcome, we can resolve them by using techniques such as chaining and open addressing. But what about the applications of hash tables? They can implement multiple sets like database indexes, associative arrays, and data structure sets.
Great. So our next data structure is one of the most easy ones to understand, and it is trees. It's really easy to understand given the name because it's where data is organized hierarchically and linked together. So it's different from a linked list though, because a linked list is in terms of a linear order. But we're mainly going to be focusing on binary search trees in which the binary tree's data is organized in a hierarchical order, storing values in assorted order.
So let's define some variables. The value stored in the node is known as a key. Left and right is where the pointer is pointing. And finally, P is the pointer to the parent code. So the application of trees are that these binary trees can be used to implement expression solver, while binary search trees are used to search applications where data is constantly moving in and out. And another important application is heaps to store Java objects.
And speaking of heaps, it's also our seventh data structure we are going to be talking about today. So heaps is a special case of binary tree where values are arranged based on the comparison between parent and children nodes. So heaps can be represented by both trees and arrays, and there are two types. First, we're going to be talking about the min heap property, which is when the key of the parent is less than or equal to the key of the children, and the root contains the minimum value of the heap. Our next type is the max heap property, and that is when the key of the parent is greater than or equal to the key of the children, and the root contains the maximum value of the heap.
So what are the applications of heaps? They are used in heap sort algorithm and are used to implement priority values based on the heap property using an array. They can be used to find the smallest or largest value of an array as well.
And our last data structure for today is graphs. So a graph consists of a set of vertices and edges. And the order of the graph is the vertices, while the size of the graph is the edges. So we're going to be talking about two main types of graphs, which are direct and indirect.
So direct graphs exist when all edges have a direction indicating a starting and ending vertex. Self-loops are part of direct graphs because they are edges from a vertex to itself. Then undirected graphs exist when all edges have no direction, and it can go in both ways between the two vertices. They are isolated if a vertex is not connected to any other node in the graph.
And to end today's episode, here are the applications of graphs. So graphs are used to represent social media networks, web pages, and links, and locations and routes in GPS. Well, that's it for today's episode, and we thank data science for providing us with amazing information that we were able to talk about today. Look at toward data science for more information on data structures.
I hope you guys had a fun time listening to this podcast episode, and don't forget to tune in to our upcoming podcasts. Feel free to reach out through our Instagram and Twitter page at STEM Time Podcast. Don't forget to keep learning new things. See you in the next episode. Bye bye.
Bye, guys.